As most of us may have come to realize, Kerbal Space Program is a lot like a physics simulation, in the sense that a lot of real-world physics apply to it. Now, I originally created this craft, we'll get back on that topic in a moment, but this craft was originally created, as I just stated, kind of to go on the end of my Kerbal Attachment System mod spotlight. I was going to show you some silly things you can do with it. However, I found a greater purpose for this. So let's turn on the engines and show kind of what it does. Well, I have these four small Rocco Max engines attached to a pretty decent sized fuel tank, and I'm just spinning it. Now it's able to spin because I've got one of the docking washers from the Infernal Robotics. We are in 2.3.5 and Infernal Robotics is updated, and I haven't found any bugs with it yet. So as you saw, it spins and friction eventually stops it. Now I'm going to open up the GUI from these winches that are part of Kerbal Attachment System, and we're going to extend them a little bit to see how this changes. Now I want to extend them to about 1 each, 1 meter. Try to keep them equal, and let's turn the engines back on. Now if you notice, instead of remaining the same shape they were where they were falling toward gravity, they've turned and become perpendicular to gravity when they're spinning around. However, if I cut the engines, as you can see, gravity starts to take hold again, in which case they become parallel with gravity instead of perpendicular. Now, I found this interesting when I first witnessed it, because this means that centrifugal force is being applied to these, and it's working accurately like it does on Earth. So, let's extend these some more. Let's speed these two motors up, and I want to extend these to about 8, I think. See if I can get my point clear. They don't need to be even, just close enough for balancing reasons. Oh, exact, okay. But let's turn the engines back on. Now, if you notice, when I turn the engines on, the winches are moving faster in the direction of the rotation than the fuel tanks. Like if you notice, they're kind of lagging behind it. Well, this would imply that since they have more mass than the winches, that they're adhering to momentum. Well, I didn't think that Kerbal Space Program would apply momentum in such a way that this would show. However, it does. So let me keep throttling these rockets up so they get faster. And I'll just go all out now, full throttle. And momentum does occur. Now I need to slow these extend down and start extending them. Now if you notice, with these engines full throttle, these two fuel tanks, these small fuel tanks, are remaining perpendicular to gravity, meaning a force is constantly being applied to them by this spinning object. Now I'm going to stop both of these from extending, even them out a little bit, and as you can see, we're kind of going at a set pace, and it's accelerating very slowly. Well, you can tell angular velocity is definitely there, along with momentum, because, well, I haven't actually shown momentum yet, but you can tell that momentum is being applied because the fact that these fuel tanks are lagging behind. But now they're pretty much lined up with the winches, meaning everything's all set. Now, I want to show you why I find this so intriguing. Now these are set to the max retract speed, and I'm going to start retracting them. And cut the engines. Observe. This thing is speeding up how quickly it is spinning. The engines are cut. How would it go faster if it's got no more thrust to continue its speed? It's spinning a lot faster than it was. Now friction is taking over and slowing it down. But why did it do that? Why did it speed up? This is because angular momentum was conserved. When these fuel tanks were far out, about 20 meters away from the center of mass, which would be about this command pod, these fuel tanks had a huge moment of inertia. Well, this whole object had a huge moment of inertia, in which means that the further away these are, the more moment of inertia this has, meaning the more force it needs to spin quickly. And when we brought the fuel tanks in, it began spinning faster because its moment of inertia was severely decreased the closer these two fuel tanks got to the center of mass. You see this with ice skaters when they have their arms spread wide open and they begin spinning, and then they bring their arms in close to their body. They decrease their moment of inertia, in which case they begin spinning faster. And this is a real world physics thing, a real world physics, law, I guess, calculation you can do. And it exists in the Kerbal Space Program. I never expected this. However, I do want to show another example. So let's go see that. Now, this example is a little more difficult to accomplish because I can't do it on the surface of Kerbin due to the weird friction. However, let's see what happens. Now, I'm going to start up these engines, and we're going to see this thing starting to rotate and the whole kind of odd landing leg craft oscillate. I'm just going to let this build up a little bit more speed before I begin. Now, these different hooks, all I'm going to do is take this servo hinge, the powered hinge, and I'm going to bend it. Now, engines are cut, which means that's spinning as fast as it will spin. And oops, that's the wrong one. Let me start spinning that again. Okay, this is the right one. Now this is going to get pretty fast, and watch. Engines are cut, and I'm just rotating this. So what is this? Why is it spinning? Well, this is another rule of conservation of momentum, angular momentum. Conservation of angular momentum. When you cross, well, I'll start with this. Basically, all momentum of something spinning has to be conserved. For example, this is still spinning as it was. However, part of the torque that was causing it to spin has been transferred to the center docking ring, which is right here, which is causing this whole thing to spin when it prior was not. Now, what I said about crossing is you can cross torques, which is what I just did. I changed the orientation of the torque from being under this axis, which in space there's no real name for it, but from being under this axis of this thing spinning to turning it under a perpendicular axis. I was crossing the torque, in which case causes some of the angular momentum, or all, well, some of it, because Kerbal Space Program actually doesn't do this perfectly, so if you were to calculate it, it would not be accurate, but some of the angular momentum is conserved. So in theory, the Kerbal Space Program and concept applies conservation of angular momentum, and that is quite impressive, seeing as how it's a game built off of code and not a real world application, or exactly being a real world simulation designed to simulate something like this. This is designed to launch spacecraft and land on the moon. It's meant to have fun. Yet it adheres to a real physics concept. And I'm going to show one more example that I found really interesting about crossing the torques in just a second. This is not necessarily the final test, but this is going to be kind of a preview for it. Remember how I mentioned when ice skaters extend their arms and they bring them back in? Well, I created a couple pistons from Infernal Robotics to show this. So I'm starting them extended. I have a couple of engines with some small fuel tanks, and I'm going to fire them up. Now, as you can see, that I can get it spinning pretty quickly. Now, cut the engines and retract them. As you notice, it spins a lot faster. Now, the final test actually has to do with why this is starting to wobble a lot. Because as you see, let's bring them back out one more time, and full throttle. This time I want it to go faster, and extend them, or retract them. Do you notice how the whole frame starts spinning violently? Well, this is actually what I want to show. So I'll be back when I hop in space. So now that we're in space, let's take a look at this one more time, except without the surface gravity. Now, when we get it spinning at a decent speed, and we cut the engines, and then bring it in, it spins a lot faster, and our whole vessel begins to freak out a little bit. Well, let's see if we can get it in this try. For the most part, we do have it. Now, if you notice, this vessel is spinning. However, when our large lander leg vessel, this is two parts, there's going to be our kind of pendulum part that spins, and then our landing leg part. That's going to be the base vessel with the landing legs. But if you notice, when the base vessel is spinning like this, the little pendulum, and it's not really a pendulum, but I can't think of a better name at this moment, isn't spinning as quickly. Now, see if I can't use some of the unrealistic torque from our command module to quell down the rotation enough to time accelerate. Okay, there we go. Now that it's sturdy again, let's try this one more time. Except this time I'm not going to retract it. I'm just going to start it spinning and cut the throttle. Now, what I'm going to do is, this is doing it on its own, or at least doing this much on its own. Now, why does it try to do this? Well, this is because it's still trying to conserve angular momentum. So, for example, when this base craft is spinning, then if you notice, our kind of pendulum piece, our baton at the end, at the top of the vessel, is not spinning. So I'm going to fire up these engines again to get this thing spinning. Now, it's not going into a perfect rotation, but here we go. This is what I wanted to see. Now, if you notice, the baton piece is not spinning. Well, now it is, but it was not spinning back there. I want to see if I can get into that state again. Now, you can see that the baton piece isn't spinning all that much. Now, the reason for this is because all of the momentum that the engines are providing is getting pushed into spinning the larger base vessel with all the landing legs, as you can see. And then when the base vessel stops its spinning speed, as you notice when it comes around this way, the base vessel spins slower and the baton starts spinning itself. This has to do with the way momentum is conserved when you cross the actual axes of rotation. Now, the previous tests didn't work very well. However, I'm going to show you what I was attempting this time. Now, if you notice, I have my vessel here with the arms extended on the baton, and I'm going to throttle up. Now, as it's spinning, the faster it goes, the whole vessel begins to oscillate a little bit. And I went to an extreme here because it seemed to work better at proving this. But if you notice, since the entire vessel with all the landing legs is spinning, the baton is not spinning. The baton is actually stationary relative to the vessel instead of spinning perpendicular to the vessel. Also, if you remember from just previously, the way this vessel was oriented, it's spinning in the exact same axis of rotation because the baton actually moved perpendicular to how it was and started spinning the entire vessel the same axis of rotation. Now, this is actually really interesting because I was planning on crossing them, but this didn't actually cross the rotations. Since I was only adding rotation and not any torque, that would actually cross the rotational inertia, excuse me, once I think of words. This is still conserving it. And if you notice that this whole vessel was spinning slower than just the baton was when it was spinning by itself. Now, I'm just using some torque to slow this down, and I'm only using one direction of torque, or I'm actually going to use 2 eventually. But basically, I'm just trying to get this to a stop, because in theory, if we were to stop this thing's rotation, even though the command module torque is a little bit cheaty against real-world physics, if we were to stop this thing's rotation, then in theory the baton should start spinning again, because the rotation would have to go somewhere. And if you notice, I'm going to turn SAS on to stop this. But if you notice, the baton is spinning very slowly. Now, we did lose quite a bit of rotational momentum from the torque of the command module, because, like I said, it doesn't really adhere to real physics. But this thing, now that it's spinning, is adhering to real physics. And what I'm going to do in a moment is just retract these, and you can notice that with the decrease in the moment of inertia, it begins spinning a little bit faster, just like in real-world physics would. However, I am going to end it here, because I hope you all liked the video. I also hope that you kind of get what I'm saying, understand the whole moment of inertia, conservation of angular momentum idea. It's really interesting in physics because you can kind of steer with it. Like if you've ever seen a physics demonstration for it, then you'd see let's say a student would sit there and spin a bike tire perpendicular to gravity, and then he'd be sitting on a free rotating plane, and as he turned the tire from being perpendicular to parallel with gravity, he would begin to rotate along what he was sitting on. However, like I said, going to end it here. I am PTTGRW, signing out.